Hello again. This is me, Roger Alexander, founder of Cathodic Protection Network. In this video, I want to clarify how we measure cathodic protection and the effects of cathodic protection on corrosion on a steel pipeline. Right. I have drawn here the measuring circuit. So this is the voltmeter, and here is the copper sulfate ground contact electrode. The measuring circuit is through the test post to the pipeline, oops, and then through the earth to the electrode, right? So it's the path through the earth that causes the complications. You will have been told that this error is the IR drop in the measurement. That is very short-sighted. It totally ignores the reality. If the electrode is put over the cathode of a bimetallic coupling, a lump of metal with copper and steel attached to each other, buried somewhere in the ground. You put your half cell over that. If you put it over the cathode, that will become part of the measuring circuit that is reflected on the voltmeter. Other things that can affect is a generator, which is not earthed properly. It is earthed off balance in its star. That will create either a negative or a positive effect in the ground around it. Also, high voltage cables running over the top will give AC voltages to the ground. Not necessarily to the pipeline, but to the ground itself. So if you have your half cell put over an area that is affected by high voltage cables, you will see a AC charge, and that will cause differences in the readings on your meter. But that may or may not affect the pipeline and pipeline corrosion. Another thing that I've experienced and created and demonstrated is the telluric effect. Now, this was originally thought to be all sorts of causes, and it's sometimes due to geomagnetic effects and things like this. And it's sometimes mistakenly called the effects of sunspot action. But what I have found and proved is that you can cause a static telluric effect in the ground, and if you put your half cell over that, you will get a different reading to putting it over virgin ground or natural ground. So what I'm saying in this video is that we have to think of the measuring circuit as being the measurement of the whole of the pipe steel, including the effects of anodes and cathodes, corrosion cells on that steel pipe, some of which will have a larger cathode than anode, Some will have a larger anode than cathode. Some of them will have the anode and cathode combined in one coating fault. And then, of course, we have sacrificial anodes buried, and they will affect the whole of the pipe potential. But also, if you put your half cell anywhere near these, you will obviously get the effect on the ground, which will be included in the measuring circuit. So, in order to illustrate the problem, I will now show you that we measure corrosion, and this is a corrosion cell. It's a rechargeable battery, and I don't really know how much charge there is in this particular battery because it has expired and it is an unknown value to me. And as you can see, whoops, it's only got 23 millivolts in it. Let's try, switch that off, take this out, put this one in. That one's got 36 millivolts in it. This is the potential difference between the carbon rod and the steel case of the battery. We'll try this one. This has got 17 millivolts. Now, if we measure one of these in here, we can say that the 1.6, yeah, just a minute, yes, 1.6. We can measure the potential difference between this side of the battery and that side of the battery, and the energy contained in that battery by the chemical reaction in the battery is negative 1.6 volts, and volts is a measurement of potential differences. Okay, and if you remember, Gibbs free energy says that there can be no such thing as zero potential, and therefore there is no such thing as negative potential. And it's just that the meter says it's negative. So if we change the connections on the meter, we will see that it's now positive. So this proves in one fell swoop that Gibbs free energy is correct, and that we have to think of cathodic protection in an entirely different way. We have to know that the meter is telling us the data. The display on the meter is telling us the data. Right, now we come to the next problem with our way of measuring things. And, oh dear, I think I've got this set up a bit wrong. Right, I was going to show you with two batteries in series, but I can't do that because the connections are wrong and difficult to change. So, I will show you with three corrosion cells in series. Oops. So this is 3 corrosion cells in series, and they give a total voltage of 4.03 volts. Potential difference between this and that. This input in the meter and that input. And you get the same thing if you use a digital oscilloscope, or if you're in a laboratory, a CRT oscilloscope. Okay, so this is the way that we measure corrosion. Now the problem is that we have 3 values and we only want to know what one of these values is, and that is the value of the corrosion cell on the pipeline. That is, we need to know the value of that and that. According to DIN 50918, which is the laboratory specification for the measurement of the corrosion reaction and electromotive forces, we have to have the probe close to the anode. It has to be at the anode without disturbing the anode. But we haven't done that. We've just simply put connected to 3 sources of energy, and we don't know what the one on the pipeline is. There's no way of telling. Now, if you think that this represents the corrosion on the pipeline, this represents the telluric effect, and this represents the half-cell reaction itself, how can we analyse that reading? We can't. Okay? Now it gets even worse, because as the sketch showed you, there are more often than not a lot more influences, and some of them are fluctuating. Whoops. I've got to put this up a bit to here, I think. One moment. Oh, damn. Right, now we have 8 corrosion cells, right? So we have 8 unknown potentials in series, and they give us 9.64 volts. So if we think about the influences that we are trying to measure and to analyse, we have the transformer rectifier, which is pumping charges into the ground. We have telluric effects. We have high voltage cables. We have bimetallic couplings. We have generators off star, and we have sacrificial anodes. And 1, 2, 3 coating faults. So that means that we have the number of influences on this meter now is 1, 2, 3, 4, 5, 6, 7, 8. So how do we analyse, how do we gain any data from taking the measurement in this way? We can't. It's rubbish. And this is the reason why I invented the Alexander cell, which itself is a corrosion cell that we can put in the location, and that will give us the amount of corrosion that is going on in this area. And when we connect it to the pipeline, it will show whether the pipeline stops the corrosion in the Alexander cell. This can be tested when you're on site by arranging for the transformer rectifiers to be switched on and off, and you can see the current in the Alexander cell altering according to the adjustments to the cathodic protection system. Okay? Hopefully this has cleared up the matter of what we are doing when we are taking pipe to soil measurements.